And then we'll hear the final word on HOL Light.
Okay, thank you for giving me the space to give this presentation. So yesterday I gave a little introduction how to use the system, what it's like to write a little proof. Today I will just explain the foundations of the system. Everyone always says it's small. Well, it takes me 10 slides to explain it, but after this. So the plan for today is the first part is the logic, how the terms and the types and the theorems work. The second part is the implementation of the kernel, which implements the logic, and the third part is how tactics are implemented. So there's a lot of different things, and if you get lost, just ignore what I'm saying. Okay, so HOL Light is just lambda couplers, simply type lambda couplers. With two extras. One is that there are constants, and the other one is that it's weakly polymorphic, so we have the alphas are not base types which are fixed, but they're variables. But there's no quantification over the type variables.
So if I can be evil, this is very computer science. If you are
this is very logically. I mean, I'm wearing my lambda calculus shirt today. Lambda calculus to me is the computer scientist.
I'm talking just about the notation.
Oh, the notation. Okay, let me explain the notation then for people who are not computer scientists like me. Okay, what is the whole typer? This is some kind of context-free grammar notation, and if you're a computer scientist, you don't even think about it. So it's very good that you keep me honest here. There are two kinds of HOL types. The green alpha means it's a type variable. And in HOL there generally capital A, capital B when you're using the system. And you can substitute for these type variables arbitrary types. So it's like a variable but then for types. The op is a type operator that takes a couple of types and makes a bigger type out of it. And I give some examples in the white space which I left open, but if I put everything there together I cannot point anymore to the grammar. So I'll give examples of that later. A whole term is basically four possibilities. Either it's a variable, it's a constant, it's two terms next to each other, and that's you should read as function application. So t is the function, and t prime is the argument. And normal people put the bracket one place to the left here, would say t applied to t prime. With lambda calculus people just, and functional programming people put it next to each other, and then they're happier. And this is lambda abstraction. This means we have a function, it takes an argument x, and the value of the function is this term t. And that's all we get. This is the whole system. So yesterday I had this term type and whole type. The values of this are these things, nothing else. But then we write down the prime number theorem. That doesn't look like this kind of stuff, right? So here are some examples. So the natural numbers, well, then the op is none. No arguments. It's a constant type because 0, it's zeroadic. The Booleans, same thing. Functions from A to B, the type of functions, is a fun or type operation with two arguments. Okay? List is a typical thing that you would give a type argument. That's the type of list with elements in A. So this is examples of this instances of this grammar that are kind of meaningful. Then of course I also have examples for terms. So normal people would write function with two arguments like this. If you're a Haskell or ECTA programmer, you don't know about commas, so you write it like this. And how does this match this grammar here? Well, function application associates to the left. So later on I'll omit these brackets, but this is the structure. We have a constant, we have a variable, we put them together, we put another variable, we put them together. Right? X plus y doesn't look like function application, but really it is function application written in infix notation. We have a function plus, that goes from natural to natural to natural. I apply it to 1x, then I have a function. So this is partially applied plus. It means if I do the plus of 3, that means 3 plus x, right? And then I have equal, exactly the same. So normal logic makes a difference between terms and formulas. Terms are the objects and formulas are the statements. In HOL it's all the same. If a term is type bool, it's a statement. So x is equal to y, or for all these terms here have type boolean. And so for all, where's the for all here? Well, that's a constant. Constant for all. So exclamation mark is the, and it's really the name of the constant inside the system. It's not that it's syntax for all, it's really the string for all. Okay. Now to make it a little bit more complicated, actually the name x doesn't determine the variable. It's the combination of the name and the type. And the same for a constant. There are different constants with different types and they're not the same term. So it's like this. And then there is a notion of correctness for these things. If I take the number 3 and apply it to the plus, that doesn't make any sense. So the types of these terms should fit together, and you can put that in the grammar by annotating everything with the type. And the sigma 1, sigma 2 is the same as the sigma here. So a type of type sigma is a variable of type sigma, a constant of type sigma. Here it needs to be a function type applied to, okay, and if I put this in my examples, this took me half an hour to get this right, you get lots of types everywhere. Okay, clear how this works? So those variables are like in logic free. If you're type serious, you want them in a context. These people are not type serious. They're just free variables. Free type variables, free variables. There are two infinite sets in HOL. It's the set, in the implementation, it's the set of ASCII strings. But if you're more of a logician, you would say x0, x1, x2, or x prime, x double prime. Infinite sets, it's kind of available. For the constants, it's different. There is some kind of signature, or some kind of state of the system, and you work over this signature. But the signature grows when you define new types and constants. Then there's more available. Okay? So that's different. It's not that you can just talk about any constant, because the constant needs to get the right type for the constant, right? So in my example here, it's really, I cannot put exclamation mark for any type. It needs to be the for all exclamation mark. So it needs to have a type like an instance of this type over here. So a function, a predicate, this is the type of a predicate. It has a truth value. It needs to be the same. So in the environment, there will be this exclamation mark with that type, and you're only allowed to have that constant there. So when the system starts, there are only the first row of this table. Signature for logic, there are only two type operators available, bool and fun, and they're not needed to write down the logic inference rules, so they're kind of the core of the system. And equality. So dependent type theory runs on application, lambda abstraction application. Although these are lambda terms, HOL really runs on equality. Apply is the basic tactic in COC and Lean. Rewrite is the basic tactic of Isabelle and HOL. Okay? And then there are three actions that I'll show in a minute. And there are two more things for that. There's a primitive type int, which I'll talk about later. And there is a constant at, and those are kind of primitive. All the other things in the signature will be defined stuff. That's the idea. So what is this int and this at? So often if you're serious, bool is called omicron and int is called iota. So bool is kind of clear, that's true and false. Int is not an actual numbers, but it's like natural numbers. It's a type you get axiomatically. All you get about it is that it's infinite. It's some unknown infinite type. Okay? So there's one axiom which I'll show in a minute that says that it's infinite, and that's all you get. So in the PVS demo, it's like we can define the type, we just introduce it, and later on we might talk about it. And in Isabelle this is possible. You can introduce a constant and only later define it. In Olight, it's the same. You can only get a constant by defining it. So apart from this int and this add thing that we get axiomatically, all the rest needs to be defined in terms of these things. And add is the Hilbert choice operator. So how does that work? So you can write it like this, and the syntax is like this. If you have a predicate, I can say, give me an object that satisfies this predicate. And in some systems it's called the x dot x is bigger than 3. For instance, if p is, okay, give me an object bigger than 3. Okay? And then you get 4 or 5, you don't know what you get. Like in videos, it's underspecified exactly what it means. So this is global choice. If there's nothing that satisfies p, if the x that is false, well, you get something in the type, but you don't know what you get because it won't satisfy p, because that's not possible. That's the reason the types are non-empty, have to be non-empty. Because I have a type A, and I say add x in A false, it will be some object of type A. There have to be an object of type A. So what I said yesterday, that there are no empty types, is needed for this feature. Okay. What do we look at? In HOL, there's you can add new axioms yourself if you like. You can pollute the axiom set. So there's a function axioms, and if you run it, it will print the axioms. So if you're getting a HOLite file and you want to check that they didn't add any axioms to cheat, you say axioms, and it will print the HOLite statements that belong to the axioms. So there's infinity x, which says that there's a function from int to int that's 1 to 1, but not onto. So it uses defined constants 1, 1 and onto. And they exist. The existential quantifier also has a defined constant. That says that the int type is infinite, nothing else. Then there's select x that says that the p of the epsilon of x px, that the epsilon of x satisfies p if there is an x that satisfies p. So if you give me an x that satisfies p, then I know, and this is another way to write existential, but you can already write this when you don't have the existential definition. And then there's eta x. So extensionality of functions equality is always a bit of a hassle. If two functions have the same values everywhere, they're the same function, but you don't get that from the logic. So this one, you can add this. This is eta equality.
It's not quite function extensionality, is it?
Well, it's what you use in HOLite to prove the extensionality theorem, given all the rest. I can show you the proof in the class afterwards. Okay. What of this is, let's get to this later. Remember these 3 axioms. I will talk about constructivity in HOL in a second. Okay, these are the axioms, and now I'm going to give the proof system, the inference rules. So the things there are sequence. So we have gamma turnstile p. Gamma is a list of terms of type bool. P is a term of type bool. That's the shape of sequence, and you are going to derive sequence with inference rules. Okay. So that's the proof system. And there are 10 inference rules, but they don't fit on one slide. So this slide will have the first 8. And then I always don't know which one to start with. I think John starts with Raffle. These are basically the 2 simplest inference rules you can mention. Assume if I know P, so the way you should read this, if the things on the left side are true, then the things on the right side is also true. Assume says if we have P, we have P. Reflexivity says equality is reflexivity. That's what gives you reflexivity. Then if you have reflexivity, you expect symmetry and transitivity. And symmetry you can derive with the rules, so you don't need it. Transitivity you actually also can derive with the other rules. So you won't need it, but it's in the system for efficiency because it's used a lot. And if you need to get that from the other rules, your proofs go slower. And if you know anything about these systems, this is kind of weird, gamma union delta. In normal systems, the gamma is the same everywhere. So basically, normally these rules go bottom up. That given a context that you want to prove, it gives you a larger context above the line what you need to establish to get it. But in HOLite, it goes top down. If I know equality with from some assumptions and I know the other equality from some other assumptions, delta, and from the union of those assumptions, I get the third equality. And you really should consider these assumption lists as sets. So you could write gamma, comma, delta, just append them together, but that's not how it's implemented in the system. It used to be, but there's really, it's sorted for one application, John overhauled the system and it really behaves like sets. So trans is actually not needed, so I made it gray. Then we have that it's a congruence, so if something is, some subterms are equal, then the whole term is equal. You get that from those two rules. I don't know whether you can follow it as fast, but that's what it says. Then we have beta equality, and now André is going to say this is not a real beta equality, because you only get it for an argument x. So later, the full beta equality will be an example of something bigger that we can build from the basic rules. So if I have a lambda function lambda x dot something, I apply it to x, well that's the something again. And that's the beta group. Then we have reasoning. So equality, because it's on booleans, is really equivalence. That's something that typeface like coming from Agda and Kok also will find very strange, but it used to be that it always printed like equality. At some point I complained about it and we changed the printer that if the arguments are booleans, it prints as an equivalence. But this is just, like I said, this equality is the single constant that we have at this point. That's why we have equality as constant. This thing is really the constant equality applied to the variable p. Okay, so this is modus ponens, but not for implication, but for equivalence. Okay. And then there's the strangest rule among the 10, deduct anti-sim rule. And this is a crazy rule, so let's make it blue because it's crazy, and also make it blue because my next slide explains why it's this way. Okay. Deduct anti-sim rule, and one slide about it. So if you're a natural deduction person, these are the two rules for implication. You have modus ponens, error elimination, we already saw it for equivalence, and we have error introduction. If I need to prove P implies Q, I assume P and I prove Q. I add P to my assumption list and then I encode it. Okay. We have versions of this for equivalence as well, because we don't have implication, we only have equality, and that's equivalence. Okay? So equivalence really has two versions. I can put P, go from P to Q. This is the left, but because symmetry was one of the derivable rules, I only need one of them. This is the EQMP I just showed. But the other one is introduction. If I from P I can derive Q, and from Q I can derive P, then I can derive the equivalence. Okay? So let's do that in the top-down style, where with the gamma and the delta. That the gamma and the delta don't need to be the same. So if from gamma and P I can derive Q, and gamma Q implies P, then from gamma union, this is the same thing, but with different assumption lists for the Q and for the P. Okay, but this is still not how it's in whole life, because all these rules, the assumption list above the line are just gamma delta. So let's give these things a name, gamma prime and delta prime. Okay? And now you can see where the anti-sim rule comes, deduct anti-sim rules. This is gamma prime, this is the rule I already had, and it's not exactly the same, because if gamma contains P, then, I mean, here I wrote commas because I started from something that's familiar to natural deduction people, but I really should have used unions. But if gamma already contains P, of course this is smaller, but that only makes it more bold. Okay, so this is the equation of this weird rule that Joseph was photographing. And then we have two more rules, because I only had 8. Instantiation. You can instantiate, simultaneously instantiate variables and type variables. Like I said, if there's a type variable, then you can instantiate. And now full beta reduction is an example of something you get without. So we can only get beta reduction for a variable, but then we can instantiate the variable and we get full beta reduction. And this is implemented in the system as a derived rule. It's called beta const because you give it this term here, and it's, if you remember from yesterday, for yesterday you give it a term and it gives you an equality. The 3 plus 4 conversion gives you 7. The beta conversion, if you give it the beta redex, gives you, and it's only at the top of the term, it's not inside the term, there's another conversion for that. Okay.
You probably explained the square brackets.
Yeah, this means there's a term that contains an x, and then we fill in, replace this x everywhere with u, but not when it's bound with an x. This is called substitution. I could have written it with a substitution operation, but I took the whole light menu of version 1.1, and there it's like this. So that's all. Okay, these are the rules. We have 3 axioms, we have 10 rules. Way to go. Okay, so the missing part is there are 2 ways to extend the signature, to define stuff. And for terms, it's really, for term constants, it's really easy. If I have a term, I can abbreviate it as a name. That's the only way in which we can define a constant. Okay, that's easy. Then to define types, that's really not easy. That's there's the deduct antisim rule and this thing. Those are the 2 difficult things. So let me read it, but on my next slide I have a picture. So let's go to the picture component. If you give me 4 things, you give me a type, sigma. You give me a predicate on the type, something that cuts out part of this type. It can be true on some elements, it can be false on some other elements. Okay? You give me a constant in the type A, and you give me a sequence that's been proved that P holds for A, so A is inside the part of the type that P delimits. You can define a new type called op that corresponds to the part of sigma where P holds. And I have a picture on the next slide, so that makes it easier. And then you also get 2 functions between the new type and the old type, ups and rep. Ups is the function that maps elements of sigma to their abstract version in op. Rep is the function that maps part of op to a representation it's an abstract version from sigma and a representation from the abstract type. Okay, and you get 2 things proved that basically tell you they're like inverses. And again, if you want to understand it, wait for the next slide. So basically, what do you give to the system? This is a horrible part of the system. You give it 7 things. 7 things. You give it a type. For a type, you give it a term. You give it another term. You give it a theorem. You give it 3 names because you want to know what the names are. And what do you get back? You get back that these things are added to the signature. You get 2 sequences. So you get back the modified the state of the system plus 2 new theorems. So this is crazy. But now we done that, so let me show the picture here. The op is really the subset x in sigma. Subset doesn't mean anything, but that's just informal talk. So we have sigma, we have part of sigma, that's where P is true. Inside this, because the new type needs to be non-empty. I just told you it needs to be non-empty. And then we get functions ups that goes on the whole sigma. If it's outside this little blob, you don't know where it goes. But if it's in this blob, you got the corresponding element of this op type. The representation function is more meaningful. And then the 2 axioms tell you that it's like this. Okay. What of this whole, so now we have 3 axioms, 10 rules, of which 1 is not needed, and 2 definitions mechanism. What is constructive and what is not? The whole light sources are wrong. There is some comment in one of the files, constructive logic of classical logic starts here. And that's not true. 2 of the axioms are fine. Only the choice axiom is wrong, constructively. But extensionality, if you interpret everything with setoids, that's fine. There's a nice indication. Yes?
Can I come back to this example? So how is this? I'm trying to figure out what happens when P is the false predicate.
Then you cannot prove P of A. If you remember, one of the parts you needed to put in to get this is a proof that A satisfies P.
Oh, sorry, I see that one.
Okay, so here something fishy is going on. If I take something here and I go back and forth, I map it into this P. That's something that constructively won't work very well. So this type definition thing is not constructive. And the choice axiom is on all the rest if you interpret everything with separates. So this is before this comment in the sources. So, and these two axioms are after this comment, so it's almost correct.
Sorry, this is part of the foundation.
This is the last slide about the foundations. We're now done with the foundations.
I mean,
You have seen everything.
this is built in. This is not the right.
This is one of the rules. So if you would be a logician, you would have judgments with an environment and a context. You could write it like this. Yeah. This is the end of the story.
Because, for instance, substitution, beta conversion, you could do that.
I showed. Yeah. Okay. So this is pretty primitive as definitions go. But all the stuff you would want, you can define in terms of this. This is a primitive, like with the statements I said, okay, we have only these weird lambda terms, and internally that's just what the statements are. Similarly, everything you want, so this is all there. Num was taken, but not was not. So you can type this into the system and the system will be fine. I mean, you can say define type not and it will return to theorems, an induction principle or a recursion principle. If you call that last one not recursion, you can have recursive definition over it. You can all the stuff that functional programmers want and people who want to prove stuff about it, it's there. In Isabelle HOL, it's really, which is exactly the same logic, it's there on steroids. So Jasmine Blanchette and so on, they formalize the categorical definition of inductive and co-inductive types using only this primitive basis, and then they have a whole world where you can get anything you want. If you haven't seen it, look at it, it's really beautiful. So this slide really belongs to my yesterday talk. This is features of HOLite as a user. This is not part of foundations. But because you might get the impression that it's primitive, it is inside the engine, but you can build a pretty powerful engine. Okay, summary. I said this a couple of times already. Second part of the talk, how is this implemented? Okay, you saw the grammar on slide 1. This is OCaml code. This is the grammar on slide 1. It's exactly the same thing. It's a bit strange that abs is what abstraction is, what lambda is called. That's a term, not just a variable. It doesn't matter. I mean, they also could have put string times Wiedijk there and it would have been a variable. But, okay, so if you go to the HOL sources, there's a file called fusion.ml. It's not about cold fusion. That has these definitions at the top. And why is it called fusion? It used to be the case that there were 3 files. Type.ml, term.ml, theorem.ml. And that had the definitions for those things. But this is inside an OCaml module to make it abstract. I'll have a slide about that later. And an OCaml module needs to be in one file. So he concatenated these 3 files, called it fusion, because it's the fusion of 3 files, and it's still called fusion. In case John is watching this, hi John. I'm sure he will be watching this at some time. There is double space after this tie-app. That has been there forever. I don't know whether it's intentional that he leaves it or that he doesn't care. Similarly, there are brackets around this, while there are not brackets anywhere else. I don't know. Okay, this was for John. Okay, so for all n is bigger or equal than 0. I think that's true in the natural numbers. And I don't need to say that it's a natural number because the bigger or equal knows it's a natural number. The type inference will figure it out. I got a term. We had this yesterday. But I can turn the pretty printing off. Okay, I don't want you to pretty print terms for types. And now I can do the same thing. And now you can see in memory it's just a 3 data structure. It's just const type, well, the thing I did on my first slide that I figured out myself how to make it into brackets, that's the parser of HOLite is that doing that for you.
Is it using the OCaml conventions for infix operators?
I think the infix stuff is all. Yeah.
So
HOL
if you
is.
have an operator, if you have a name that starts with less than, it will behave like a less than infix operator.
I think there is some primitive rule for when something looks like an operator. If you put brackets around it, it behaves like a normal
Yeah,
operator.
okay, that sounds like the OCaml convention.
OCaml is a derivative of ML. ML is the scripting language of LCF, and HOL is a derivative. Those are all the same, come from the same culture.
But the pretty printer of HOL, like its inner syntax is not the same as OCaml syntax.
It's a different parser, but the conventions are very similar. If you want to put it back, you should do install printer, but I would have liked to put it here, but my slide already, if you notice, the font is smaller than the other slides. Okay, so I told you there's this module HOL, the kernel module. There are two modules in the system as far as I know. One for Metis, because that's ported from Joe Hirt's version of Metis, and there's a module around it. Maybe there are more modules that I don't know about because these things tend to change, but last time I looked there were two modules. And module HOL is the kernel. So how does it work? Well, you can make, using this syntax, you can make terms that are not well typed. And you don't want those. In Coq, there's the const type, I don't know what it's called in Lean. It's just an OCaml type, you can put whatever there's no one forcing you. Then there are the environments that the treatments like this. But here, if you type a term, because you want it to be a well-typed term. So how does it work? Well, these functions, varconst, comp, and apt, the constructors of, where is it? The thing, those four type constructors, they're inside the module. You can look at them, they're exported that it's like this, but if you try to call them, it will tell you, no, you're not the kernel, you're not allowed to do this. And the module exports four functions, make var, make const, make comp, and make app, that does it for you, and simultaneously checks that everything is typed correct. So I have a little example here. If I say I want the bool type, true, the value of the bool type, it would be like this. That's basically a T with a bool subscripted. And then it says, no, you're not the kernel, not allowed. But if I do make const, and I don't even need to type this bool thing, this is a substitution for the type variables, but the bool doesn't have any type variables. It will look a bit in an environment, yes, this is one of the constants that you're allowed to make, and then it tells you, okay, here it is. So that's how it works. The CM thing is not private, it could have been private, but it's abstract. You don't know what it is. It's an abstract data type, if you know what it is. There's a function, that's theorem, that really allows you to take it apart, to get the assumption list and the conclusion, but that's not how it's implemented. And the only way to get things in this data type is by certain functions that the kernel exports. Just like this make var, make const, make comp, and make apps that are exported, there are functions. And what are those functions? These. And it's exactly the story I've been telling you about logic. 10 rules, you can have axioms if you really want them. Two definition principles. And as you can see, this is kind of a complicated thing. This theorem here gives you both the P and the A, because this is just the thing that proves that A satisfies P, and from this you can get what A and P are. Okay, so this is how you know that when this kernel is correct, the whole system will be sound. At least will be sound according to the rules of the logic. You cannot fake it. Of course it's OCaml. There's object magic, and you can just poke the memory and you can fake it. And my wants is check it to be separate, which is fine with me. But if you don't cheat, it's not possible to accidentally cheat. Okay, and then all the rest of the logic, I gave you 10 rules, but you want to do all the logic rules. The one I had this long table that's implementing the system, they're derived rules. Basically, it builds parts of this derivation in stages. And this is the example that is beta. So here's the beta implementation. It first tries whether this is a variable already. Then it just calls beta, and else it's taking apart this and then calling instant beta to prove it. Yeah. Okay. And natural deduction, the dish tag and the match MP tag and so on that I described yesterday, they call things. If you start the basic library, it's calling millions of instances of the basic rules underneath.
Is this actually how it's implemented?
This is copy paste from the source. Yeah. If I considered leaving out this first rule because that is
So
more. What?
The beta in the first line of the body, that's something more primitive.
The beta, okay, it's good that you ask. Is that beta? Vol beta term that's exported from the kernel, it's a kernel function. And that implements the beta rule that was a couple of slides back and I don't know.
The one with the variable.
Is there one with the, yeah, but beta has an argument. It gets a term as an argument. The term that you give it is the left-hand side of the equation.
Yes. And it would fail if it's not of the correct form.
That's how it works. So the kernel function, all these things check that all the conditions of the logic rules are met. So it needs to be of the right shape. But like error introduction, all the other rules I already showed are implemented like this in many stages. One time I took, there's a video somewhere on the web from Toronto, I took the proof of 1 + 1 = 2, the famous thing from the Principia, right? And I did all the inference steps that it calls. For the 10 rules, I took 10 colors, and then I put it in some spiral like a long playing record. And it's a nice picture.
This is not doing what that derivation is showing.
Why not? Well, the first rule I could have taken it out, but then I couldn't have said it's copy paste. The first rule says if this is a variable, I don't need to do this. The second rule actually is not copy paste from the source because I replaced the A actually as arg, but I wanted this to match up with this. It says, okay, you give me a term, that's this term. The F is really this whole beta thing. A is the argument. That's comp is okay. Then V is the bind var of F. So this F doesn't really match that F. And then it says, okay, do a main comp of FF. So that's this one. And it gives you this thing, that's this beta rule. And then you instantiate A for V. So you replace this V is under the lambda, so it's not substituted. So it is doing what it says. Only the thing I didn't notice when it because F is not just this F, it's the whole. Yeah. Okay, tactics. Third part, I hope you're still with me. What is the state of, I'm in the middle of a big proof in Lean. What's inside the system? There's a lambda term. We're doing Curry-Howard. There's a proof term. But it's not done yet, so there are holes in it. It's a term with holes. That's the state of, and you in Coq, I'm sure you can do this. You can print the proof term and it will give you the proof term with the holes. You can just do it. In HOL it's different. What it is, it's just a list of subgoals and then a function that if you give me theorems that correspond to those subgoals, it will return a theorem for the thing I started out with. So this is how tactics are implemented, and I go into some more detail. But if you understand this, you understand how it works. This is a condensed version of a full quarter course in Nijmegen. So the students need to show that they understand this. And some do, but some don't. Okay, so what is the definition? So we had this four types for yesterday. Term, type, theorem, tactic. Right? This tag was implication of some function that maps to type. What is the definition of tactic? If you go to tactics.ml in the source code, this is copy-paste. This is really copy-paste. And it took me a long time to wrap my head around it. There is a goal state and a goal stack, and a goal state list that looks like a list of subgoals. The goal stack actually is just for undo. And nothing to do with the logic. It's like, okay, these are the states we went through. So refinement. Okay. So this is not understandable. So here is a simplified version. And this is actually how it was in the original LCF version. So what did I simplify? I took away the labels in the goals. So goal the assumptions can have labels. No one uses that. Well, sometimes people use that, but not often. Took that away. There are instantiations. A whole proof can have meta variables, and you can instantiate that meta variable to the proof. That makes life a lot more complicated. Then the refinement and the goal stack really don't matter so much, and then you get it. And then there's a big difference Here I have the term, and there I have the theorem. Theorem is kind of nice if you want to program the system. Let's do the simple version. This is the simple version. It's still a lot of stuff, so let's do substitute it and go to this. And now I have something that I can keep in my mind at once. So what is the goal? The goal is just from these things I need to prove this. And it's exactly the same as the theorem type, if you look. And once I had, in my course, I had someone, oh, that's useful, I can use the same type for it. No, that's not the point. This is outside of the kernel. These you can make yourself. You can just put a goal together if you like. The theorems are inside the kernel. You can only get provable things there. And then what is the tactic? Well, if I run it on a goal, it gives me a list of subgoals, it produces some subgoals, and then it does, if you give me theorems for all the subgoals, it gives me theorems for the original goal. Okay? That's how it works. So forget about this. Let's look at intro, Wiedijk, as an example. This is my last slide, by the way. This is computation of the source, and that's really complicated, so and also it doesn't match the term theorems here. This is the simplified version that people can understand. This is how you implement intro in the system. So, how does that work? Intro for implication, not for all. Let's repeat the thing from the last slides. These are the definitions. So I input a goal, which is an assumption list and a conclusion. It produces a list of subgoals. Well, with intro, what you do is you take the assumption list and put the antecedent. So the list in the code is the opposite order of the assumption list that's printed. And then you keep the same conclusion. You only do the conclusion as the subgoal. And then the thing that justifies it is the discharge rule, which is the implication introduction rule. Okay, so how does it work? Suppose I have this as my goal. I want to prove P implies Q. So I'll run this tactic and it will give me, as a subgoal, the green part, this thing. Okay? Plus this blue function, that's kept. It's not run yet. And all those functions will be combined together with composition. And when my whole proof is done, at that point it's all run. And then, during the running of this, some other function in this chain of functions will tell me, oh yes, I proved Q for you, because that's what you asked, with some context gamma prime that I'll talk about later. And then you run the dish function. So this is implication introduction top down. Just like with the anti-sim thing. And there is a typo here. Oh, that's bad. There should be P implies Q here. I'll fix that before I send it out. Ah, this is embarrassing. This is P implies Q. And then this gamma prime needs to be a subset of this assumption list, and therefore this gamma will be a subset of that assumption list. And because you started this, all the time you have that this is a subset of this, but you started with an empty assumption list when you set up your goal. So then you know that the theorem you get back at the end matches the goal. Okay, you probably didn't follow this anymore, but you're excused. Okay, I wanted to keep this as my last slide, but because of this error I won't do so. So I'll just put a green picture here.